We have introduced the notion of a quantum bit, so now know how we can store information in quantum systems. But next we need to think about how we can manipulate this information over time. And for this we are going to use quantum gates. So the idea will be again to break down the steps by which we want to manipulate the information into smaller steps. So quite generally, we will have a quantum state at the beginning, say an initial state. And then over time, we would like to change this into a final state. So we change the state of the system over time and therefore also the information that it represents. And this then can be, for instance, interpreted as a computation. Now in quantum systems, we basically have two ways to change the state of a system. One is by the time evolution with the Schrödinger equation, and the other one is by measurements. Now the measurements are mainly to read out the information, while the really interesting things involving superpositions and entanglement really occur during the normal time evolution described by the Schrödinger equation. So the process by which we get from the initial state to the final state is really determined by solving the Schrödinger equation for this system. And I write this down here in a general form, and first going to exploit a very general feature, namely that this entails a linear relation between the initial state and the final state, involving the time evolution operator, which is a unitary operator. This arises from the fact that the Hamiltonian itself is an observable and therefore a Hermitian operator. Now this operator here can be defined for any kind of time evolution, including situations where the Hamiltonian itself depends on time. But for the case that the Hamiltonian does not depend on time, we can write it down in a very explicit form, namely as an exponential of the Hamiltonian, with this time here being the time that elapses between the initial state and the final state. In a system with n individual qubits, this would be a transformation between curly n different possible input states, say the computational basis states, and curly n different output states. So this time evolution operator is therefore a curly n times curly n dimensional matrix. We can also use a graphical representation for all of this. So we could say that we have our initial state and we transform it like this. And these are all valid ways to represent this unitary operation. In this course, we are going to make use of all of them. Another striking fact of this general relation is that it can be inverted. So we can always write our initial state in terms of the final state by just using the inverse of the time evolution operator. And this can be indeed achieved physically for many systems by reversing the processes by which they evolve, for instance by changing the sign of a magnetic field acting on a spin. So therefore any computation in a quantum system in principle will be reversible. And furthermore, this time evolution is of course continuous. So for instance, we could change the quantum state just a little bit. The last fact is important because if we now think about the different ways that we can transform the initial state to the final state, the situation is much more worse than in the classical case. And there we already had a very large number of possible ways to transform the initial state to the final state. Because now we have a continuum of ways to transform these states. These are not even discrete operations. These may be all sorts of rotations in these Hilbert spaces. And nonetheless, it happens that we can simplify the task again by breaking down these steps into discrete operations, and these we call quantum gates. And furthermore, we will only need a very small number of them, in particularly only unary and binary gates. To be concrete, I'm going to call the unary gates single-qubit gates. So these would be gates that transform an initial state of a single qubit into a final state, So simply change the amplitudes alpha and beta into, say, alpha prime and beta prime. And this will then always be represented by a unitary operator u. In this basis, we can of course look at these states also just as ordinary vectors. And in this case, we just have here a unitary 2x2 matrix U. So this would be a 2x2 matrix with 4 matrix elements altogether. Furthermore, because this transformation is linear, we can completely specify it by determining how it acts on the two computational basis states, which in terms of vectors are given by these unit vectors here. And the results are simply the rows of the matrix U. So this is simply the result of the matrix multiplication of the matrix U by one of these basis states. And because of this simple structure, we can also interpret this matrix U as a kind of a truth table. For this, we are going to record the basis states in Dirac notation in a table here, and the results on the other side. And when we look at this, we see that all the matrix elements appear in a very systematic way, namely almost as in the matrix U itself, but simply with a transposition. And this transposition arises because here we write the results as a column, while here they are just organized as a row. So we can very simply read off the matrix U from a truth table as given here. For the single qubit case, we can write down a very general expression, and we can also look at some specific examples, and both is very instructive. I'm going to start with the general expression, and this is relying on the fact that any unitary operator U can be expressed as an exponential function involving a Hermitian operator A. For instance, for the case of time evolution by a Hamiltonian that does not depend on time, here we had simply the Hamiltonian times time divided by h bar, but such an operator A can simply be found for any given unitary operator. For the case of our single qubit, we can express this operator A as a 2x2 matrix in the computational basis, and furthermore write it as a sum of the fundamental Hermitian matrices, the identity matrix, and the three Pauli matrices X, Y, and Z. And in there we have one coefficient in front of the identity matrix, which I'm simply going to call A. And for the other three coefficients, I'm going to extract a factor phi over 2, so that the remaining contributions can be interpreted as the components of a unit vector. So these would be the components of a vector of unit length. Inserting this expression here, we simply then obtain a corresponding 2x2 dimensional unitary matrix written in the following form. Where we interpret all of these terms here as a dot product between the unit vector and the Pauli matrices. Next, we are going to exploit that this combination indeed has one very nice mathematical feature, namely that it squares to the identity matrix. This can be seen in several ways, including by just writing this as a 2x2 matrix, which will look like this. And multiplying this matrix by itself. But I'm going to show you a slightly different way. And for this, we are just using the properties of the Pauli matrix. So if we simply multiply out all the terms, then we are just going to rely on some of the simple properties of the Pauli matrices. Namely, whenever we multiply a term with the same Pauli matrix, then that Pauli matrix squares to the identity matrix. So we get 3 contributions nx squared plus ny squared plus nz squared multiplied by the identity matrix. And then we have expressions where x is multiplied by y, but in two possible orders. And these two orders cancel simply because xy plus yx, as an example, is equal to 0. And this applies to any pair of Pauli matrices. So we don't get any further terms. And finally, because this is a unit vector, this here is just 1. So indeed, this matrix, as specified, squares to the identity matrix. Then there is just one more step, and this is to use the definition of these exponential functions here. Because now we have a function of a matrix, and again, this is defined as a power series. So we are going to use the definition of the exponential function as a power series with powers x to the k multiplied by the inverse of k factorial, and this runs over all non-negative powers. So we are going to express this exponential function in terms of its defining power series. And in there we will encounter even powers and odd powers. Now, given this identity here, it is convenient to separate this sum into the even powers and the odd powers. Some powers k of the exponent in here. By the definition of the exponential function, each factor will contain factors 1 over k factorial. And then we have the powers of the exponent, in which we have a term minus I phi over 2. So these are these powers given here. And also powers of these expressions here. Well, when this is an even power, this will indeed just reduce again to the identity matrix, because any pair of matrices can be paired up into an identity matrix, and you just multiply these identity matrices many times. And for the odd powers, you will then simply have one original matrix left over. So here we simply have this expression. Here we now have just sums that only involve numbers, and they coincide to the definition of the real and the imaginary part of an exponential function with an imaginary argument. So this simply becomes the cosine of phi over 2, and this becomes minus I times sine of phi over 2, multiplied simply by the identity matrix, or this combination here. So this is the general expression that I wanted to derive here. As it happens, this has an alternative interpretation in terms of the state on the Bloch sphere. So when we have the polarization vector, which is the expectation values of x, y, and z, and then apply this unitary transformation to our quantum state, we transform it to a new polarization vector that I'm going just to denote as p prime. So this will correspond to a certain rotation on the sphere, and as it happens, the rotation axis will be aligned with our unit vector n, and the rotation angle will simply be phi.